Hello everyone. We are on the day 8 of our challenge solving 30 deep learning projects in 30 days. This week we will be focusing on CNNs, which is convolutional neural networks, and computer vision related projects. The project for today is to build a simple CNN for CIFAR-10 image classification. We have already explored this type of data set in our, I guess, day 5 problem. So that is good. Now let's start. Also, the flow of the problem is going to be same. I'll iterate it again. uh, we will take, I'll go and take help from ChatGPT, ask me to give me the code, explain what CNN is in easy language and everything. This is me documenting myself coding and learning machine learning from scratch. So get along with me if you want to, if you're on the same boat, have interest of learning machine learning. So yes, um, and I'll go, and I'm planning on using the same context window as I have used for my past day 7 problems. So let's start. Here it is day 8, and here is the min. Also, this is week 2, and week 2 emphasize to exploring CNNs and computer vision. So let's wait for ChatGPT to generate the response. And yes, so it says that diving into convolutional neural network is a critical step in learning how to handle image data and exploring computer vision tasks. Okay, the CIFAR-10 dataset is perfect as this is as it is a well-known dataset of color images divided into 10 classes. Yes, we know that. Uh, images are of 32 by 32 pixel, and they are what they are divided into 10 classes. There are going to be total 60,000 images. The size is going to be 32 by 32. They will be tagged to categories like airplane, birds, cars, etc. We will use TensorFlow and Keras to build a convolutional neural network, which is well suited for handling image data due to its unique ability to capture spatial representation in the data. We still do not know how this convolutional network works, so we will explore that first before coding. So it very well it is explaining, but if not, I'll ask again. So it says that CNN uses convolutional to learn from images. They are particularly powerful for image processing because they can detect edges, textures, patterns, and object party as they go deeper. The basic components of CNNs are a convolutional layer, extract important features from the layer, images, pooling layer, reduce the spatial dimensions, that is downsampling, to reduce the compilation load and prevent overfitting. Okay. Fully connected layers to perform the final classification based on the features extracted. I do understand what they are trying to say, but I do not want to jump and code, as I've told you. Let's do what? Let's ask ChatGPT to explain it with the help of an easy example. So yeah, can you? I am still clueless on of CN. Can you please explain in easiest possible way with maybe with examples or images if possible? So I do have the paid membership, so I can ask for the images. You need to have the paid membership from ChatGPT for it to generate the images. I don't know if it is going to generate some images or not. I don't think it is going to, but yeah, it is not. No benefit of buying the membership. No, I was kidding. So yes, I don't know if you could hear me or not. I don't have the mic connected. I'm using the built-in mic. But yeah, it says that using a real world. Okay. So what is convolutional neural network? A convolutional neural network is a type of deep learning model that is specially designed to work with images. Okay. CNNs can see patterns in images just like we see our image. We use our eyes and brain to recognize faces, objects, and everything around us. That is really cool. So it says CNN, convolutional neural network, are a type of deep learning model. They are really good at working with images. They can see the patterns in the images the same way our eyes see the pattern and recognize the face, objects, and everything around us like a plant. Let's think of a CNN as a series of layers that each work together to identify features in an image, much like our brain processes visual information step by step. Okay, imagine you're looking at a picture of a cat. Okay, how do you know it is a cat? Well, your brain processes the picture in parts. You might notice the whiskers, the eyes, the ears, and the shape of the face. Correct. So when I notice uh, um, whiskers, when I notice an eye, when I notice ears, for example, if I go here, not this one, this is a cat image. How do I know this is a cat image? My brain sees these cute eyes, my brain sees these whiskers, a puffy face, and these ears and a tail, and it thinks, okay, it resembles to a character called a cat. So that is why in the same way neural network, convolutional neural network work. It breaks it down into parts to decide if it is a cat. Okay, then how CNNs work? It works layers that process the image step by step. A CNN is composed of a series of layers. Okay, let me go and see how CNN, not this CNN, CNN model, and I want to see how they look. Anything easier. Okay, it has multiple layers. That I can see. This is better. Input layer, hidden layers, output layer. This is the worst. Mm, this is better. So it has many layers. Layers, layers are like this. Input layer, convolutional layers, which are to have feature extraction, then uses pooling, and then produces the do classification. So it has multiple layers that we can see. Each layer is like a specialist looking at different parts of the image, and each getting more and more detail. And here is how it works. Step one is input image. So let me go and draw an image like this. Use the draw.io. So first one is an input layer. Yes, it says. Then the first one is an step one is input image. Input image. Yes, think of an image as a big grid of numbers. For a color image, each pixel is represented by three values: red, green, blue. Yes, imagine an image is like a big piece of graph papers filled with numbers, each number representing the brightness of the pixel. Let's convert it into uh, a number. Okay. uh, what I'm trying to say, I'm trying to visualize. Let me pin it. And it's going to be CNN model. Let me go to the Wikipedia, maybe. And here I was talking about Keras, right? Keras, a prerequisite. I was talking about not Keras. I was talking about Kaggle. So I talked about it that go through this convolutional course, the basic course, and not this one, Kaggle, learn computer vision, the basic course. Here we see that not now. It looks like this, yeah. In input image, input image in grid numbers. Okay, so image will look like this. An image can look like this, and then paste here. Allow, not this. Numbers. Okay, and the image can look like that we saw. Okay, now it says the number image will look like that, where each number will represent the brightness of a pixel, like this. Okay, I will copy it and show it here. um, I don't know how. Let me not waste any more minute on this. So we saw that a picture can look like this, where each number represents the brightness of a pixel. So the first layer is the input image. The second, then we have the layers of CNN. The first layer will be the convolutional layer, which is also called as detection. Convolution is like scanning the image through all a small window of filters. Imagine like taking a small square magnifying glass and move it over different parts of the image to look for something specific, like edges. Um, like. We do not have it here. Let me do what? Uh, CNN. Yes, this is what I was talking about. See, so here the images are looking like this. So consider the image looks like this, the image that we have downloaded, and we have a filter of, let's say, 3 by 3 size, which is covering 1 2 3 11 12 13 21 22 23, and we move that filter from grid to grid. I mean, one row at a time, one column at a time. First we are covering this, then we will cover these three, then we will cover these three. Okay, now what is happening? uh, we are using these magnifying layers on our convolutional on the image, such that we want to extract the features, and we have multiple layers. One time we are extracting the ear of the cat. One second time we will be extracting the eyes of the cat, that the second layer. So that is what ChatGPT is trying to say, that imagine taking a small square magnifying glass that I had talked about, moving it over different parts of the image to look for something specific like edges. Okay, Real life analogy it is that think of convolution as a cookie cutter. Imagine you're trying to find if a cookie has chocolate chips or not. You use a small cookie cutter tool to move around and find pieces of chocolate. This tool keeps over moving different parts of the cookie image, and each time it detects a chocolate chip, it marks it. NCNN filters moves over the entire image and create a new version of the image, moving where showing where specific features like edges or colors are detected. Correct. So it uses those filter to extract the features, that is, create a new version of the images showing those features, those edges and the colors. Then we have and these are going there are going to be multiple hidden layers, multiple convolution layers. Then the layer 2 is the polling layer. Polling is like simplifying. Let's mark it has here. Then we have convolutional layers. Convolutional, not view. Convolutional. Convolutional. CONVO layers. And it is going to be multiple layers. And then we will have a polling layer. Okay. Polling layer is to what? Polling layer is to simplify the images. Polling is like simplifying the information to make it easier to process. Okay. And after detecting the features that are from the convolution layer, we want to make our image smaller while still keeping the important parts. Okay. Real life analogy will be analogy. Imagine you take a photo and then want to keep the important details. Okay. Max pooling is like using a tool to find most important piece from each small section of the image. Let me show you Kaggle, computer vision. Let me show you this, not this one. See, yes, this was the course that I was talking about. See how it is taking the input image, applying filters like this, and then producing the output. This is what a convolution layer is doing. Now, and this is what each layer shows, extracted features. And maximum pooling that we are going to talk about is clearly mentioned in this basic course to learn the computer vision. Okay, let me go back here. And yeah, so it says that max pooling is like using a tool to find the maximum important piece from each small section of the image. It helps reduce the size of the image and focus only on the most important features, prominent features. It's like shrinking an image but still being able to tell what is in the picture. We keep the significant details. Okay, so it says that it's like, so with the help of max pooling in this pooling layer, we extract the maximum prominent features, the features that actually matter. So let's do what, let's go back to our diagram, and then here we will do what, input image, then we apply convolutional layer to do feature extraction. And then we have pooling layer. What we have understood, it is for what, it is for simplifying the image, by simplifying the image by doing what, by applying maximum pooling, getting the maximum prominent features, important features. And then we have third layer, which is flattening, converting it to a list. After convolution and polling, we end up with a smaller images containing key information. Yes, we will end up with smaller images, many images containing the key information. Like if I talk in the reference of this image, for an ear, for eye, for whiskers, so it will contain a lot of smaller images. So we need to flatten that. Flattening is like taking that shrunken version of the image and making it to the list of numbers that we can feed to the final decision layer. Okay. Why do we want to flatten it? Because our neural network understands a list, not an image, not a grid. So we need to flatten it. So, imagine you take all the important pieces you found in the image and put them in a single row. This step turns all the detected features into a long list of important points. Okay, and then we have flattening layer. This and we do this to what? Convert the images, smaller images, into long list. Okay, this is it. Then we have uh, fully connected layer. After flattening this flattening step, we need the list of numbers into a we feed the list of numbers into a fully connected layer, which acts like a decision maker. It, it looks like the entire list and decides what image most likely is. What would be the real life analogy? Imagine that after seeing whiskers, pointy ears, and fluffy tail, your brain says, "Aha, this must be a cat." Yes. After flattening, we saw important features, and you say, "Okay, let's group together and then say what it is." I see an important features whiskers. I see an important features fluffy cute face. I see an important feature like a tail. Then I say, "Oh, this is a cat." So the last layer is fully connected layer, which is to make the decision from the important points, long list of important points, of important points. Okay, then we have the last layer, which is uh, fully connected layer. Fully connected layer, which is to do what? Which is to do what? Um, a decision maker. Decision maker, that is decision maker. It identifies the object, right? So this is the full neural network, how it works. Putting it all together, we put all these layers together, we get a convolutional neural network, and here's how it processes the image. Input image is an image of a cat is given to a CNN. Convolution layer extract the features after applying filters to the image, like the basic features, edges and colors. Pooling layers, the network simplifies the image by keeping important information. Flattening, it takes the pooled image and turn it into a list of key features. And then fully connected layers. The CNN looks at the list of features and decide whether it is a cat or the. Now the CNN will take it look at the list provided with the step 4, and then will decide whether it is a cat or a dog or a bird or some other object. Why do CNN work well for images? Very good question. So, images have local patterns like the arrangement of pixels in edges or texture. The convolution layer of a CNN are good at detecting these patterns. So, basically, CNN is really good at detecting pattern. So, a picture of cat is always going to have similar patterns. So, that is why an object of similar nature are going to have similar patterns. So, that is why CNN works well. Layer by layer detail. The deeper you go into a scene, the more detailed the network's understanding becomes. Early layers might recognize basic shapes like lines, while deeper layers recognize complex features like eyes or fur pattern. Okay, so it is like layer by layer we are detailing. And how CNN learns, let's look at some examples. Imagine you're teaching a child to recognize animals in picture. The step one would be you first teach them to look at simple shapes, maybe pointy ears, whiskers, and a tail. Okay. After that, you help them combine those shapes into more complex features like, yes, recognizing the pointy ear and a fluffy body mean cat. Finally, finally, They learn to say, okay, that's a cat. So this is the same way a cat, I am teaching a kid that how do a kid know that it is a cat. I'll say, okay, look at the tail. I'll say, do you see the whiskers? Do you see pointy ears? And if you see all of those, it is a cat. Similarly, convolutional layer is performing the similar way. Early layers, they recognize simple features like edges. Middle layers recognize patterns, and the final layers convert those patterns into the final decision objects like cats or cars. So we do understand how and what this convolutional layer looks like. Let's close all the tabs which are not required. So let's go back to the code and then start coding. We do understand what CNN looks like, how many layers it has, and how it functions. So let's start coding. Let's come back to the PyCharm and create a new file for today's code, today's problem, sorry. And it is going to be day_8.py. Add it to our Git repository. Mention the problem is this, okay. And let's import the libraries. So we are going to import uh, import from tensor TensorFlow Keras datasets. Import CIFAR-10 from TensorFlow Keras models. Import sequential from TensorFlow Keras models. Import a convolutional, not models, I've repeated it actually, layers. Import convolutional 2D, and then max pooling 2D, two dimensions. Flatten it, flatten and dense layers. We will talk about each layer later. Then we also need a layer called Keras, an dropout layer. Um, just a second. I guess yesterday we did understood about the dropout technique, right? Not yesterday. In day 6 problem, when we were talking about the technique to control the overfitting, we saw that there are two techniques, dropout and regularization. In the dropout, we talk about that how it can randomly drop out some neurons from the layer, so that it controls this and it prevents this overfitting problem. So we, for that we need to have import this layer. Now we will do what? From TensorFlow Keras utils, import to categorical, and then we will import matplot as plt because we want to visualize how it looks. Now let's load the data set and pre-process. So we'll say load the data set. How do we load it? We will load it like x x train, y x train, x validation. I'm so sorry. Y train, y validation, and load the dataset from CIFAR dot load data. Now let's print this x underscore train dot shape. Sorry. Let's see what is there in the validation dataset. The training target, the target list for R, validation dataset, and let's run it. Day 8. Okay. So the data set is like, okay, so data set is like 50,000 images with uh, yeah, with 32 by 32 pixel size. It has 50,000 images as the validation. Here it is the validation Excel. Okay, so it should be y, the order should be x train, y train. The next one is the, this one is for the features list. This one is for the target. So here it is going to be x train, x validation, y validation, and here it says I have an error with the function call, print function call. Now I'm going to clear the terminal and run it again, and here it should be, we have X-train is of size 50,000 images with 32 by 32 pixel size. Where then we have 10,000 images for validation, again of 32 by 32 pixel size. Then we have 50,000 um, target, and then we have the label for validation. The validation target is for, is of 10,000 size. So it is coming correct. Now we'll do what? Do you want to see, I mean, should we see it in the form of wireframe, as in the form of data frame, to see what is in the, what is in the actually, what is in the uh, this data set? We have, we saw this when we were doing it, like when we did the day 5 problem, we saw how it looks like. So should we see it? Let's skip it for now. The data looks like the all the this 32 by 32, this image. So how many rows does it has? It has like, sorry, let's see, I'm fumbling a lot. Yes, let's visualize it later, as in how the data looks. Maybe I'll decide if I want to, if I'll feel like, because I've already done it in the day 5 problem, so I don't feel like looking at the data. If someone wants to go, so they can go and check out the day 5 video. There it is clearly mentioned. But we can do other things, which is pre-process the data. How do we do that? First, we will normalize the data set. How do we do that? These images are in the range of 0 to 0 to 255, representing red, green, blue color for each pixel. Now what do we want to do? We want to convert them into 0 to 1, so that it becomes easier for the model to train. So normalize the data set, or we can say normalize the pixel values between 0 and 1. Okay, so we'll say x train is going to be x train, we will divide it by 255.0. Y, sorry, x validation will be x validation divided by 255.0. I don't think, why do we need it today? We never needed it on the day 5, so I'm going to go ahead with keeping it simple, like we did it on the day 5. Yeah, yes. So we have normalized it so that our model is able to train it faster. Now what we are going to do, we are going to convert the labels to categorical form. For that we need to see the label, how it says that the label looks like what. If we see that the CIFAR data set in, it looks like this. The labels are airplanes, birds, and car. I think the labels are already in the form of 0 to 1. So we do not have to do apply one hot encoding here. So for that, what we can do, we can see converted into pandas data frame. It will be pandas. So for that, import the library. Import pandas as pd, and here it will be pandas dot series. Here we mention y train dot shape, not y train dot 0, and and I remember I did a fumble on that day when we converting what. Yes. So if we go here, is there is a argument called flat. If we apply dot flat, we can convert it into a normal, you know what, a flat 1D array, so that Panda can easily convert it into data frame. Panda needs it in 1D vector. So we say the label is label, not here, label. And now let's see this data frame, and if we see how the data frame looks like, let's wait. Yes, see, it already is in the form of 0 to 10, so we do not have to explicitly convert it. And if you want, we can convert, see the what we can see. Hang on, I'll copy the code here of day 5 to show you how the data looks like. So we'll do what? We'll copy it, paste it, uncomment it, but do comment this line. So what we are doing here is we are reshaping, because you saw that the shape of the training data is, the feature list is of 32 by 32 pixels. So we need to convert it into 2D array. So it is going to be 32 into 32 into 3. So we'll convert it into, reshape it using the reshape function, and then simply pass it into our panda.data frame function to create the data frame. And then we did the same as we did, just did to visualize, see how the target looks like. So let's run it and see. So how many columns it has? It has these many columns. It has 32 into 32 into 3. If I do this, it is 3072, not this. Yeah. So it has 300 to 3071 columns, and each column is now coming in 0.0 to 1. Now if I uncomment it, and you would see why we did that. I'll clear it, the terminal, rerun the script, and then see the values are in the form of 0 to 255. See. So that is why we did that normalization. Now I'll comment this and comment this, so, and then move forward. Not here. Let me clear the terminal, move it a little down, and then enter lots of spaces so that we have ample amount of space left. Also increase the font size. I think this should be clear here. Now we'll go to this section and see what do we need to do. So we do not have to convert the labels here. So we will skip this step. Now we will define our CNN model. So we will do what? Define the CNN model. So the model is going to be, store it in the model variable, and it's going to be a sequential type. We will add first convolutional convolutional layer. first convolutional layer is going to be, so we have passed model dot add convolutional layer, and here we pass, let's understand it first. Here the convolutional layer has 32 filters of 32. How many filters we want? We want 32 filters. Okay. What is the size of the kernel, or the magnifying glass that we talked about? It is going to be of size 3 by 3. The If you remember, here the size of the kernel, the size here is going to be 3 by 3, the filter size that it is going to apply to the image. So with 32 filters, the size of the filter is going to be 3 by 3. Activation function, we all know why do we apply it. And the input shape is going to be 32 into 32 into 3. So let's add it. So how many filters you want? 32. What is the size of the filter we want? 3 by 3. And the activation activation is going to be rectified linear. Input shape is going to be 32, or what we can do, x train, sorry, x train dot shape. Here, if I comment it, and if I do what, I will run a thing. I'll say I want to see what comes in the shape of extreme. So I'll do what, run this thing. We already saw it, but I just wait. We want to see something. It shows this. Now if I want to see this, what it will present? 500. Okay. And 1. And then I'll say, okay, now I'll say start from 1. Don't include the 50, 100, the rows. 50,000, sorry. So it will return this. And this is going to be the input size, right? So I'll go what? I'll mention it instead of hard coding it into the input shade of our convolutional layer. So let me now scroll it down. Yes, let's uncomment this as well. Now we have added our first convolutional layer. Now we need to reduce the special dimensions of the feature maps by taking the maximum. Okay, so we did saw that how we apply pooling. We apply pooling. Why do we apply pooling? If we come here, we apply pooling because we want to simplify the image by extracting the maximum uh, important features. Okay, so how do we do that? So we mentioned that we want to reduce the special dimensions of the feature maps by taking the maximum value of 2 by 2 regions. Okay, so in what regions? Here if we go, what I have understood, here I'll go and say in this. Now let's say I've got a filtered image. Now after that filtered image, what I'm going to do, I'm going to get the maximum value out of a 2 by 2 region, out of a 2 by 2 grid, by using max pooling. So that is why we are mentioning this max pool, to mention that we want the maximum value out of a 2 by 2 grid. So add a layer for max pooling 2D, mention the region size, pool size and the strides. And then the next step was to apply flattening, so that we can convert the smaller images into a list, so that the model can be trained on it. So we apply a flatten image, model dot add flatten, and then we will do what, model dot add or dropout. Why do we add dropout? Because we want to prevent overfitting, and then this technique will randomly drop out the uh, uh, neurons, so that it prevents overfitting. And how many neurons we want to randomly drop out? 50%. And if you want to understand more, you can go to the day number 6 problem. Here we have in detail explained and understood how do these techniques work and why do we apply them. um, Now we have added the dropout. Before the dropout, we need to create the fully connected layer. We did not do the last step, which is the decision maker layer, which is a fully connected layer. Connect based on the list here, as in identify the patterns. So we'll add. Before that, let's add dense. How many neurons you want? 64 neurons you want. Activation function we want rectified linear unit. We added the dropout already, and then we are going to have the output layer. The output layer is going to be a dense layer, and the how many neurons you want? 10 neurons. Why? Because we have 10 classes in the CIFAR data set to predict, which is ranging from 0 to 10. We already saw it when we printed this thing. Now the target. Now that is why we want 10 neurons. The activation function we want is softmax, which is used to output the neurons value as sorry, just a second, I forgot that word. As probability, and the sum of that, the probability of all these neurons is going to be 1. So whichever is going to have the maximum probability value, it is going to be the category, or it is going to be the class for that image. The model will predict that class, that category for that image. Now we will come back here. Now we will compile the model. Compile model.compile. So we'll mention the required things. We'll go ahead with the classic, the basic, I mean the go-to optimizer Adam. Then we have already understood these terms in depth in the previous videos. But if you want, you can check out which one, this day 5 video, where we have clearly understood why we are using Adam. And there are other optimizers as well, and when to use them, SGD and RMS prop. So the loss, how do we calculate the loss? We calculate the loss using sparse, not sparse. It is a category, right? Categorical cross entropy. Okay. Then we have metrics. How do we calculate the performance? We calculate the performance based on accuracy. Done. Cross entropy, categorical. Done. We have compiled the model. Now we are going to print the summary of the model. So summary. Now we will simply train the model. How do we train the model? Uh, First, whatever we are going to train on, we will store it in the history variable, and then use the model.fit function to train the model. Uh, this is going to be the data set that we want to train on, the data and the target list, the feature list and the target list. The validation data is going to be X validation and Y validation. Then how many epochs you want to run? We want to run 10 epochs, that is 10 iterations. Then in each iteration, the batch size is going to be 32. No, let's go ahead with 64 here actually. Uh, then yes, uh, uh, And now, do we want to see while it is training the output of each epoch, as in what is the loss accuracy for training and validation data? If we do, then we need to mention it with the verbose equals to 1, otherwise we can skip it, as the default value for verbose is 0. And now let's do what? Now let's evaluate the performance of the model. So if let's model the performance of the model. So what we'll do, we'll say test, store the loss, say test loss and test accuracy. Test loss and test accuracy, use model evaluate function. Here represent the x validation data and validation output, and mention verbose 2. Now I don't know why do you mention verbose 2, so let's go and read the documentation of this function. Here the auto, there are values like auto 0, 1 or 2. Verbosity is mode, 0 is the silent, 1 is the progressor. So we want, okay, so with this we want to see the progress bar, that is why we are mentioning this verbose equals to 2. Yes, so you want to see the progress bar. Okay, now we'll print the loss and accuracy. The loss is test loss, and accuracy is test accuracy. Okay, so this is done. Now we'll do what? We will visualize the performance. So how do we visualize the performance? By look per data type O, by looking at the loss and the accuracy against the epochs. So for that we have already imported the library matplot .py plot library. So first define the figure. The size of the figure is going to be 10 is to 7, and then plot the history dot. Okay, I did not do that. So first we need to convert the history to a history data frame. So for that we'll do what? Create a history data frame. We'll use pandas to create data frame of the history uh, vector. Now we will use this history, sorry, data frame, and here we will use loss. We will first look at the loss, and the label is going to be loss. This is for training loss. And then we will plot history data frame validation loss, and we'll now will look at the curve of the validation loss. And label, not lambda, label is going to be validation loss. This is for the validation data. Now we will mention the x label is going to be box. The y is going to be, y side is going to represent the training and validation loss, and I have a typo here. And then we will mention the title of this plot is going to be the training, TRAIN, training and validation loss uh, of convolutional neural network model. Now we will do what? We will print the, let's show it. Now we will print the, now we will do for the accuracy. So wherever you see loss, just replace it with the accuracy, everything is going to be same. So now capital one, accuracy, accuracy. This is validation accuracy. Then we'll have a training and validation accuracy, the training and validation accuracy of CNN. So now we are done with coding part. Let's look at how this model will perform by running the script. So let's run it. d8.py. Okay, we have an error. What error do we have? We have the error at line number 50. So we'll go here. I guess we need to flatten. Did we flatten the images first? I don't think we have flattened the images. Okay, here we have to add one more convolution layer. So first add second convolutional layer. So add it. Add convolution layer. How many filters we want? We want 64 filters now. The size of the filter is going to be 3 by 3, the kernel size. And then the activation function is going to be the rectified linear unit. We, as we have already understood it in from our previous video, that we do not have to mention the input shape after the first layer. Then we add the max pooling to simplify the image of size 2 by 2. Then we flatten it, and then we dense it, then we drop out it, and then we output it using the softmax. uh, so let's run it again and see if this will run fine now. Okay, I have error even now at line number 55. What error do I have? Model dot fit. Sorry. Let's go back and see why we are getting the error. Verbose validation data, X train, Y train, validation X validation, Y validation, epoch spatial. Why do I have this error? What the error is? It says that the output shape is incompatible. 32, 32, 64, 3 by 3, 64, 3 by 3, and then we have 64, 10. Correct. Do we have the error here? Let's check it. 32, 32, 3. And let's run it. Okay, we have the error again. I'll say Let's mention this. I don't think this should be a problem. Let's run it again. Okay, let's replace this with this thing. X validation, X validation. Let's run it. I don't think that, yes, this was not the problem. I'll keep things like they were. Alas, okay, I don't think this is the problem here. Problem is with this. It should be sparse because we have numerical categories as in 1, 2, 3, 4, 5, 6. Extreme. This. Let's run it again. Yes. See, even ChatGPT is giving me wrong thing. So it should be sparse underscore categorical underscore cross entropy because here the target values are in the form of 0 to 10 digits. They are not encoded, so that's why we are going ahead with sparse. Uh, yeah, let's wait for it to uh, do how many epochs? How many epochs did we have mentioned? 10 epochs. So it has already run uh, 4 epochs and loss started with 1.8. The accuracy was 0.32, and for validation the loss was 1.4 and the accuracy was 0. So 48%. So let it perform on all the, I mean, complete it for all the 10 epochs. And this is the summary of the model. It has these many layers. Okay. Then this is the total parameters and trainable parameters and non-trainable parameters. So this gives me the summary of the whole model. Mhm. Okay. Here we are on the eighth epoch. It is taking good amount of time. It is taking on an average 13 milliseconds in each step or 10 seconds to run one complete epoch. So the accuracy is increasing slowly from 32% to 61%. Uh, so the accuracy was not that good, but we see the validation. If we see here, the loss is 0.95. The accuracy is 66%. For the unseen data, 66%, 95%, 0.95 loss. 61% is for the on the accuracy is on the training data, and the loss is 1.06. So it did decrease, but it was not that great. So yes. Um, Now, if we look at the for the validation, it is slowly decreasing the loss. That is great, but then it increased for the, but it did not reach the minimum. Maybe if we would have increased the epochs, we can see the training. Uh, we can see it getting better or producing better performance. So let's take the screenshot, and if we see the accuracy should increase and should reach to the optimum accuracy pretty fast. That is the ideal expectation. Now for with each epoch, for the training, the okay, now you would be confused which one is training, which one is not. For that, we did miss the one important function called plot dot legend, and here we'll say plot dot legend, and this way we'll be able to see which line represents what. So let's rerun this thing again, and I want to do what, I want to increase the epoch size from 10 to 20. and the batch size I'll decrease to 32 so that we have better performance. It is going to take longer time. Earlier it took like more than 120 seconds. Yeah, 100 seconds, which is about 1 minute 40 seconds. So it is going to take more longer time. So you might have to fast forward it to 2 minutes. So I'm going to run it again after this changes in this parameters. Or from the last day, what we learned that we can also apply hyper tuning to figure out the best combination of the models. Sorry, best combination of the parameters like epoch and batch size and other things, and the number of neurons, everything, or the learning rate. But let's park it for another day because you want to keep it simple and sweet. So see, it is now taking longer time than the previous uh, training. It was taking 10 seconds earlier, now it is taking 12 seconds and on an average 11 seconds. And we have 20 epochs also. So yes, 10 into 20, 140. So yeah, you might have to fast forward it to 3 minutes actually. So let's wait for it to generate. If you remember, the accuracy was earlier 66% for the validation data, and something 60% for the 61% for the normal. Let's wait for it to go beyond that. Okay, and the accuracy earlier was 61% if I remember. Now it is increasing from 61% to 63, 64. So hopefully it should be better by the end of 20th epoch. So it is performing really good by increasing the epoch size. We see that the loss is continuously decreasing, which is a good sign. And same for the validation data, it is decreasing steadily. The accuracy also is also increasing from 61% to 68, uh, 69, almost 70%. So if we saw here, the accuracy was almost 70% for the training data, and for validation it was 69%, again 70%, almost 69%. Let's park it at 69%, which is really good, better than the last training with 10 epochs and 64 batch size. So, and the loss is also better here. It is lesser than the uh, last time we ran the script. So this is really good. Now we'll go here and see, look at the graph. Now we see which line represents what. The training is represented by the blue one. The validation loss is represented by the orange one. The training is steadily decreasing, the loss is decreasing, which is a good sign. Here the loss for the validation decreasing, and then we see fluctuations here. Let me take screenshot here, and then for the accuracy it should reach to the optimum level pretty fast. That is what it is doing, so it is really good. And for the validation, we see from here, we can see this is line represents validation accuracy, and we see that it also increases pretty fast, but then we see a couple of fluctuations, small fluctuations like this, but it is increasing. That is really good. It is not going down at least. So the performance is really good of the model. uh, Now let's take a screenshot and be done with it. So we have done what we have. Just we'll go back to the model. So we have uh, coded the application pretty nicely. Let's mention the training here, this output, how the model has performed. Now let's do what? Let's clear it and add the code to our repository, day 8 code. So we'll have add code for day 8 for code for day 8, and then add day 8.py. We it should be git commit. Let's clear it. Do git status and then push it to the main branch, and then we should be able to see it in our public repository. The code is here, and then yes, it is done. We have successfully built a simple convolutional neural network. It was a pretty long video because it was our first time coding this model. So yes, but it was pretty nice understanding the all the concepts related to it. So the coming videos from this week is not going to be that long because we have already understood the crux of the topic. So yes, the topic. So yes, thank you very much. We'll come back and solve the D9 problem.